Hello, my name is Mark Elliott. I am the Chief Operating Officer for Europa Science, who is the publisher of Electro-Optics. Welcome, everybody. This is the first webcast of 2025 and the first in our ongoing series of Photonics 100 webcast series, where we're bringing you the very best insights from the leaders in the field. We've got three terrific panelists today joining us for this roundtable discussion, which is about unlocking the future of spectroscopy with cutting-edge light source innovations. I know all of them have some unique perspectives on this topic, so I'm really looking forward to the debate. So I'm going to introduce them quickly, if I may. First of all, we have Hania Fatahi, who is, of course, a member of the Photonics 100 alumni. She leads a highly respected research group at the Max Planck Institute for the Science of Light in Germany. And her research group is tackling three of the most challenging issues of our time, which is obviously sustainable solutions for space exploration, addressing the climate crisis, and advancing label-free sensing and imaging. So welcome, Hania. Thank you for joining us today, and congratulations again on being one of our Photonics 100. Then we have Caterina Vosi, who is the director for the Institute of Photonics and Nanotechnologies at the Italian National Research Council. She leads on ultrafast dynamics there, and her current research focuses on ultrafast spectroscopy to study photophysics and photochemistry of molecules and materials. Welcome, Katerina. And last but certainly not least, Liam O'Fallon, who leads the nanophotonics group at the NTU Center for Advanced Photonics and Process Analysis. His research group focuses on developing efficient lasers and innovative sensors on nanophotonics and integrated photonics, and so far has won more than 29 million euros in national and European funding. So welcome to all three of you. Really looking forward to the debate. Thank you for joining us today. And a very warm welcome to everybody watching wherever they are, at home, at work, etc. I also would like to just very quickly thank our sponsor who makes all of this possible. So Hubner Photonics, which is a leading manufacturer of high-performance lasers for analytical instrumentation, as well as cutting-edge research, and especially single-frequency lasers for Raman spectroscopy and femtosecond lasers for ultra-fast spectroscopy. Welcome to them. Thank you again for your support in making this happen. So a little bit of housekeeping before we get going. Obviously, if you are watching live today, there is an opportunity to interact with us, to ask questions as we go along, or indeed to comment on what you're hearing. You can ask a question by filling in the form at the bottom of your screen. So please do. And as they come in, we will try and get to those, and I will ask the panelists to participate in the answers that you're posing to us. It is designed to be an interactive roundtable session, so we're going to have a broad debate around a range of issues and topics in this area. Obviously, if you're watching on demand, you can't do that, but you know, I hope it's still a very interesting hour or so for you to spend your time with us on. So without further delay, let's kick this off if we may. I'm going to ask a very general question of all three of you to start with, which is obviously, where are we? What are the biggest challenges involved in getting the best out of spectroscopy techniques? And obviously that could be about equipment drawbacks, cost implications, timeframes, specifications, anything that comes to mind. How would you summarize where we're at? I'm going to start with Hania, if I may. If you'd like to answer that one first.
Yeah, sure. I think we are doing pretty well, right? There are several spectroscopy techniques available in different wavelengths. And I don't know, there are several attempts to just put them integrated and on chip. But we definitely benefit from high sensitivity, high dynamic range, high specificity, simplicity. So the tools that we have are mostly complicated for laboratory scale. We benefit a lot if we can just put all these spectroscopic techniques on chip. And let's say if we would like to use them for space exploration, so it's important to have them sustainable, that in a way that you don't need external source of energy to just run your spectroscopy technique, but you can use whatever is provided to you in space.
Is customization still a massive issue for this sector? I mean, are we finding the applications and the use cases incredibly complex, or is there a general level of accessibility depending on the use case? I mean, is it getting better, I suppose, in terms of getting to that opportunity that you were talking about there, where you can use things across a range of applications?
Yeah, I mean, there are so many products that you can use these days, right, from off the shelves. But again, the highly sophisticated one that brings you exotic results you can't find them on the shelf, right? I mean, maybe Katarina can just talk a little bit about, for example, the attosecond spectroscopy, which is really important, really have a big role in our understanding of phenomena that happens at very fast scale, but the technique is very sophisticated, right? And you cannot buy it and just install it in the lab and start to do your experiment.
Yeah. Okay, taking that lead, Katarina, your thoughts on that question?
Yes, definitely. Specifically concerning adding to what Annie said and going on, considering attosecond spectroscopy. Indeed, I think that the technology is well developed, but like the costs of this equipment, like the initial investment that you need and then keeping the equipment up to date, it's really like something which is challenging in terms of making it very spread technique, and it's extremely useful. I mean, looking at very small temporal scale, but also in the XUV range. So like having chemical sensitivity of the spectroscopy, this can be very useful. But somehow one has to think about maybe larger scale facilities or let's say infrastructures lab at the, let's say, level of universities and let's say public research institution to provide some tools, so spectroscopic tool to the community, also of companies interested, because at the moment the technology is not ready, let's say, to be, let's say, on the shelf. So this is definitely a point. I would add also concerning the training of people, like many very advanced spectroscopic techniques really need high-skilled people. And so we need continuous training and up-to-date training of like a good community of scientists that can deal with that. It's like several advanced spectroscopy techniques are not something which is really accessible, like an instrument that it's ready to use. And this at the moment, it's a challenge. Yeah. I think that's not only applying to attosecond, I would say, but it's applying also to other spectroscopic techniques, even like visible spectroscopy, which is kind of on the shelf, but still to do state-of-the-art experiment and maybe application that are needed now for some of the problems that you also mentioned in the introduction, like for the Green Deal. I mean, we need to characterize new materials, but then we need to characterize also devices like in situ or in operando. This is not something that it's on the shelf and needs to be developed.
Okay, Liam, thoughts?
Yes. I'd say one of the biggest challenges is getting spectroscopy systems out of the conventional photonics lab, which is both an issue of cost, robustness, the analysis, the electronics analysis equipment is also not small. So it's the systems currently are very complex. And back to Katarina's point as well, they need a skilled operator at the moment. In principle, spectroscopy and photonic sensors can be quite user-friendly, can be compatible with field use, but we're not there yet. We need to reduce that need for the highly skilled person.
Okay. It's often the way, isn't it, where you have a ambition and it hits reality very full on when you've got people involved and really practical kind of, considerations about the environment, for example, that the technology is going to be used in. I had a general question, if I may, just quickly, before we move on from this topic. From your experience, when either you're working with teams, your teams you're working with directly, or from what you perceive to be the issue, further afield with other companies, when people are looking for a spectroscopy solution, are they going into this with their eyes open? Do they know what problems they're going to face when they come to you or start exploring the options, or are they surprised at some of the things you have said, where actually it's about training, or it's about you really got to think about the environment it's used in? Are people going in with their eyes open? Liam, I'll go back to you, if I may, on that one first, and then work round.
It varies. Maybe, let's say, in the air quality space, it's probably maybe the end user is more informed, knows what's involved. For dealing with, let's say, food samples and similar, they can be very surprised at the answer you give them and what's actually involved in taking the measurements. Cost of the laser is also can be quite shocking to people, depending, especially if you're going to the mid-infrared spectroscopy range and dealing with somebody who's familiar with the UV visible. So there can be orders of magnitude difference in laser cost in those scenarios.
Okay, Katerina, I saw you nodding. You can go next.
Yes, I think I can fully relate. I think that the first step is kind of the setting of a common language. Sometimes we really have different expectations, different competencies, and having, let's say, a wide point of view, it's not easy. So the first starting point is usually to discuss in order to find out really what is the problem, how to tackle it, and then find the most suitable spectroscopy. And sometimes here I would say that be people looking for a solution, they don't know exactly which are the possibilities. But also we may tend to suggest solutions that may be, and for us I mean people from the academia or from the research institution, that may not be the best one because, as we said, of cost or versatility. So we need to set a common ground of language and understanding the problem.
Okay. And Hania, anything to add to that?
So I can maybe give you a perspective from the research lab point of view, right? So my customers are my students.
Yeah.
And what surprises them is that, so that if you present the project to the student that we are going to do this spectroscopy measurement on this sample, so then the students sometimes come with the mindset that, okay, there's a device, you push some buttons, and you put the sample. So they are pretty surprised to see that how much time they have to spend on the skill time, right? On the laser development, generation of the pulses that they need. So this is the part that maybe industry can also contribute more, because the sources that you require for advanced spectroscopic techniques are not available off the shelf. So you have to build it in your own lab, right? And then that's a bit of surprise for the students when they start, that they have to build their piece, their own device piece by piece till they reach the spectroscopy techniques.
Yeah, interesting. Yeah, I guess no shortcuts, right? That's basically the message we're hearing. Okay, right. Let's go on to some specifics. Katerina, if I could go to you first on this one. Now, you're researching in XUV spectroscopy techniques. I'm wondering about that in particular and how you find efficiency can be boosted when moving towards higher photon energies. How have you been finding that? And what are the sort of things people could take away to achieve that?
Yeah, this is a very big challenge and open question in, let's say, femtosecond technology is the main topic, because of course, we are interested in going toward higher photon energy, but also with high flux. The high flux is needed for any experiment. Indeed, from this point of view, there are now two strategies, one can generate XUV with tabletop sources and with free electron lasers. So concerning the tabletop sources, these are based on ultra-fast lasers, which is a technology that is well developed. And we recently saw a shift, I would say, because after a very long period in which the TISAF sources were the main workhorse, we are now dealing with a new system based on ytterbium, and there is a lot going on also in the pulse compression and making the sources more efficient, the laser source more efficient, so high peak power. And then, the generation itself in tabletop sources imply the interaction between those lasers and gas targets. For instance, in my lab, what we are developing now is the interaction in a microfluidic device. So this is a combination of different competencies, because microfluidic devices are usually used for other applications, but then they can be used to optimize the phase matching for this kind of generation of XUV. Of course, there are other approaches, like, as we said, the free electron laser for generating. In that case, like the temporal structure may be more tricky, and it's also less accessibility. On the other hand, of course, the flux is really huge. Those two, let's say, are complementary. Somehow one has, if one is interested in doing, let's say, femtosecond and in general X-ray spectroscopy, time resolved, then we need to use both, basically complementary, because of course free electron lasers are not so accessible, and then like from these, let's say, development. There's a lot going on also in detectors, not only on the sources, let's say, but also in detectors for directly having temporal resolution and higher efficiency. And also advanced data processing. I think it's something that is quite something useful in this kind, because I mean, the number of photons is anyway intrinsically limited, and it's not possible to build bigger facilities every time. So like one has to take the best out of the sources that are available. So from this point of view, there are a lot of ancillary parts that can be improved. And from this point of view, of course, the machine learning techniques may be helpful in the future to, let's say, provide good data analysis to extract information even from very noisy data. That is sometimes the case with our experiments.
Okay, and Hania, do you see the same? I mean, I'm not sure if this is a technique you're particularly involved with, but do you see the same thing? Recognize a lot of what Katerina is saying there?
Yeah, I mean, absolutely. So, I mean, as Katerina just mentioned, I mean, detection is important. So to be able to detect the light fully and all its characteristics, it gives you somehow power to overcome so many problems that you have with the signal to noise ratio. So one of the new things that we do, we are now able to detect the electric field of light directly in ambient air at petahertz frequencies. And this is what we are trying to employ for sensing the atmospheric pollutants, for example. That helps you with the signal to noise ratio, detection sensitivity, selectivity, and so on. And again, I second on what Katerina mentioned about the sources that we use, right? So we are using laser. So you need a bright, high flux source, and you need very good detectors. And of course, for atmosphere, it's a bit complicated, right? Because you have water, which absorbs very heavily in the infrared. So you have very particular windows that you can pick these atmospheric pollutants that water doesn't have so much contribution to not eat all the energy of your laser pulse that you have. So then it's important to have laser sources which are bright and have very good photon flux, let's say, and very good detectors at these specific ranges to be able to pick up whatever you would like to, for example, look at in the atmosphere.
Okay, and Liam, any thoughts on this topic?
No, it's just similar statements. The laser is a key building. You need light to do photonics, plain and simple. So especially over the last 20 years, we've seen a lot of progress in quantum cascade lasers, interband cascade lasers, which have driven a whole lot of driven much of the recent advances we've seen in spectroscopy. Power outputs have been increasing, bigger ranges of spectral coverage, power consumption been decreasing. So there's been it's been sort of pinned the whole field. We're starting to see drops of prices now, and there is this famous chicken and the egg that if we can if there is sufficient demand, the price will come down. If there's sufficient demand, the volume will go up. If the price comes down, there's sufficient demand. So we're starting to see that happening, and this is looking quite encouraging for the next few years. Certainly, for some of those types of the mid infrared laser.
Yeah. So it's this constant push and pull, right, in terms of the sort of the market conditions. As we've started, you mentioned obviously the atmospheric stuff. I mean, your team, Liam, works with atmospheric gas sensing, and you are, I understand, implementing indirect QPAS spectroscopy into an autonomous system. How's that been going, and where do you see it evolving over time?
So basically over the recent years, we've seen a move out of the lab. Again, probably not as fast and as far as we need to do, but that progression, the systems have been getting smaller, more compact. In particular for air quality. Air quality is basically the is completely undersampled in our cities and towns. That the especially some pollutants who will vary depending on the wind blows. If you've got a hedge or a car, you can have completely different values. So yeah, there's both a huge need for networks of high performance sensors. So I see this progression from the lab to the 19-inch rack to the shoebox unit. We've had units flying in drones, ourselves and other people have had units flying in drones, and to I see that continuing. Cost is one of the bigger issues. One of the big obstacles at the moment is the assembly of the system. At the moment, you need one person aligning and putting together all the components of your system, and of course that creates a massive bottleneck. So we need to come up with new advanced techniques, chip-based techniques, integration techniques, where we can be robotic assembly of these systems, which will go a long way to both making it far more scalable.
And Hani, obviously a lot of your research work is around, methodologies to overcome some of these issues that Liam was describing, when it's actually out in the environment doing what it needs to do. Are there kind of any overarching big wins that we've either seen or are beginning to see around how to kind of compensate for some of these bandwidth and sensitivity limitations? What are the big wins in this area, do you think, or what are you working on to try and get to those wins?
So what we are working on specifically, we are trying to somehow make sources and detectors for the open windows of the atmosphere. These are the windows that the water doesn't have very huge absorption, and it lets you to really go to high sensitivity. So we are working on this concept of femtosecond fieldoscopy, that you can really detect the electric field of light with very high sensitivity. And I know of the work of my colleague in Graz, Brigitta Bernhard, that she's trying to do somehow similar kind of, let's say, assessment with frequency comm, but detecting the atmospheric pollutants in UV, right, to look at the real electronic absorption band. So these are challenging tasks. So where do I look? I look at near infrared and short wavelengths infrared. And for example, she's trying to push the technique to UV, right? So what the complex, it's very nice because you have these open atmospheric windows at these ranges, right? You can get higher sensitivity, but then you also have the overlapping of so many absorptions of different atmospheric, let's say, pollutants. Then you need somehow, let's say you really need artificial intelligence and very heavy computational technique to separate the response and can trace it back, that what kind of pollutant with what concentration contributed to this absorption spectrum that you see. So these are exciting windows somehow that they are showing up, beside I just second on what William explained about going on cheap, integrated, powerful sources that you can take out of the lab and put it on the drone and fly. So this is really the final, let's say, this goal for all of us. But in the laboratory scale, then we are trying to explore these new, let's say, spectral windows.
Yeah, interesting. I wondered how long it would take us before somebody mentioned AI. We lasted 23 minutes. It seems to be, the universal truth that there's something going on with that kind of application, or that kind of technology. AI seems to be kind of infusing everything we're doing with, not necessarily shortcuts, but further opportunity, I guess. So look, we're all conscious there are many, many kinds of spectroscopy techniques, being used. I don't want to reel off a list, but obviously we're conscious of the obvious ones, atomic, infrared, Raman, etc. What differences should our audience be aware of between these techniques? And if they, which ones do you think work well in certain contexts, and which ones are problematic? Slightly contentious question, but I'm guessing you've all got very much on the ground experience with this. Katrina, what give me an answer to that one, please, if you will.
So I'll start with a very general observation. So you want to pick a spectroscopy technique, you need to understand which is your problem. So what do you want to study? Which is the information you want to have on your sample? Because of course, like spectroscopy is light matter interaction. So what you want to do is like the properties you want to extract from your sample, and then this obviously restricts the let's say the techniques. But then there are other points, and I mean, like there are different techniques, and I'm thinking about time resolve, for instance, because mostly this is my field of expertise and the field I work in. So even if you want to do time resolve, then you can use different spectral region, like Annie and Liam were saying about the mid-IR or terahertz, like ultra-fast terahertz spectroscopy. So it's sensitive to, let's say, charger dynamics in semiconductor. Then you can have optical spectroscopy, which is very powerful technique where the information are somehow all entangled. So you need to understand what you're looking at, because you may have, I don't know, like exciton or like lattice structure popping up. You may have like there are attempts to doing like time resolved Raman, so like assessing the vibration. XUV spectroscopy in different which is the chemical sensitivity. So I mean, there's a huge variety even in the small field family of ultrafast spectroscopy, and each of these techniques have their peculiarity. My opinion is that anyway, nowadays we need kind of an holistic approach in which we combine more than one technique, because materials are becoming so complex. Like you are looking at heterostructure for for energy production or like for solar cell. Like you really need to assess characteristics from different points of view, and this is true also for ultrafast spectroscopy. Then, of course, I mean, like depending if let's say if you are a company or if you are, let's say, a student, then you may want to consider also the reliability of the technique, because they are not all reproducible in the same way. And for instance, also complexity and cost could be something that you consider as a company, for instance. Like, this is very general, so maybe my colleague can go back to some more specific points in their field of expertise.
Okay, no, it's really useful. There's something I want to come back to on there, but I'll hold it for a bit. Liam, your thoughts on this point? You know, things to be, which ones work, which ones would you avoid, or is the point that you need a blend, universal?
Yep, no easy answer. A lot of our current work at the moment has been on mid-infrared spectroscopy. So that's great. It's a great technique because you can access the vibration and energy levels, which give you a fingerprint of your compounds. But as mentioned already, water is a pain. It's carbon dioxide is a pain. So the interference are the drawback of mid-infrared. There's been various proposals or dreams being able to look at the overtone bands in the near-infrared and visible. Certainly a very good technique. As you go into that region, your efficiencies drop and your spectra become more complex, which shifts the challenge to the analysis of the spectra, which again pushes you in the AI direction. And AI analysis of spectra is a very good idea. AI analysis of everything is more debatable.
Okay, well put. Hania, what are your thoughts on this one?
Yeah, I mean, I think many good points were just mentioned. But maybe like as a general comment, it depends on what your problem is, right? So if you would like to look at some electronic transitions, then you have to really go to the UV and XUV. If you are looking at some molecular vibrations, you are at the Raman or infrared. And if you want to look at some, I don't know, rotation or structural changes, then you have to do terahertz, right? These are where the fingerprints show up. Then maybe you can categorize things to linear and non-linear spectroscopy. With linear, I mean, as Liam just mentioned, so you have the advantage that the cross-section is high, right? You get a very good signal, but it comes with other problems. So if you are doing biology, for example, the water absorption is high. If you want to mix it with microscopy, the spatial resolution decreases. So then Raman, you can do it in near infrared, give somehow complementary information to the, let's say, mid-infrared spectroscopy. But then, of course, the cross-section is lower, so your signal is weaker. Right? Yeah. But then you don't have to deal with the issue of the water, but it has its other drawback. So it depends on what the problem is, right? And based on the problem, then you can adjust and choose the tool that you need.
Yeah. And are you finding anybody people are coming into these specific use cases with a kind of an inbuilt bias against or for certain techniques. Is that an issue? Do people come thinking they're only fixed on this kind of approach? Anyone who wants to answer that one? Or
these days, Katerina also mentioned many people are going towards like multidimensional spectroscopy, that you use 2-3 spectroscopy technique to have this holistic view somehow, right? So I don't know if you want to add to this, but yeah.
I suppose I find each brand or each wavelength range has its own specific problems, and you'll find an expert in building a system for a certain range, and when you change ranges, there's a whole new set of problems, so it doesn't transfer easily.
Okay, that's interesting. Yeah, it makes perfect sense to somebody not doing that sort of work myself, but I can see that. Okay, so that's an interesting segue into the next question, really, which is about the actual materials. And obviously, everything really rests on how good the kind of the equipment that you're using is. What is the quality control of this like? And has it got better? And what do people need to be thinking about? I mean, I'm guessing the context is key here. Where is it being used? What does it need to be able to withstand or analyze, etc.? But, are there any things where you think people routinely miss something obvious about the choices they're making in this regard? Katerina, I'll start with you, if I may, on that one.
Well, it's a good question. I'm not sure that we can say that there's something that people are really missing. There are, several problems. To be honest, I have to say that the premise is that I'm not an expert in quality control of material, in the sense that most of the material I study, they are like, let's say, made especially for the experiment. They are really novel material, and most of the properties are known. Actually, one of the things that we assess is, the reproducibility of this material, or maybe how those materials stand in time. So, it's not really quality control, I would say. But there are development. One that has been already mentioned, that was artificial intelligence. I think now, we can prepare databases, and we can use those databases somehow to some kind of standardization of procedures, and also to train artificial intelligence. To be honest, from my experience and my feeling in my research activities, that at the moment we are exploiting only a small amount of the capabilities of this artificial intelligence, and we don't know exactly how to include it in our tools. But it's a powerful tool, so this is something that may really impact, I would say, on quality control of materials in a way that at the moment I cannot really predict, but I think it will be impactful. I don't know if another point that was already mentioned, it's the hyperspectral, multispectral capabilities of techniques, and this is also something that it's developed, it's being developed with interesting application also in the sector of agri-tech or space, and it's going to be developed in the next future, concerning, of course, materials, but also those other kind of application.
Okay, that's useful. Hania, what thoughts on this area?
Well, I also don't have background on the quality control of material, but I'm very amazed that nowadays when you pass at the airport of this station, that we had to just open the bag, open the laptop and so on. But now, I don't know, the detectors are really improved in terms of sensitivity and specificity, that you don't have to open your suitcase anymore, right? So I think the whole industry is going on the right direction, but I'm not involved in that, so I just say that I enjoy it so much, right?
Yeah. It makes all our life easier. Liam, what thoughts on this? Are you close to some of this?
I think that hits the point nicely. Is at the moment the field is we need to move to the direction where you get your feedback almost instantaneously. The traditional way that has been done and still is being done, you take a sample, send it off to a lab. 2 or 3 weeks later, you get your answer back. It's good, bad, counterfeit, whatever the case may be. We need to bring the systems to where the samples are, where the samples are being produced, samples are being found, and get as close to real time that there's there's obvious efficiency savings if your production line is not is out of sync, out of spec, whatever the case may be. For every minute that it's in that state, you're wasting often just hot water. Sometimes it can be as simple as wasting hot water in some of these plants. If you can bring it back and bring the parameters back in line, you get huge energy savings and costs, especially in pharmaceuticals for the very very high-priced products. So yeah, I think this dream of bringing to the analysis system to the production line online is becoming more and more real. Some of the issues is the cost of the systems. I've seen some cases where the cost of the analysis system is as much as the production tool, which doesn't make sense, does it?
No, absolutely. And, I think one of the things that we're often asked when we're talking about these sort of topics is there an industry average for kind of downtime, for example? We talked about we're going offline a little bit and stuff and things. I don't know the answer to this. I mean, if you had to say what percentage of, your kind of time on any particular spectroscopy area was spent, fixing something or realigning something or reevaluating, is there a kind of benchmark we could share? Liam, I'm going to start with you again. I mean, what when you're modeling an exercise, what do you assume that kind of dead time to be in 100% of your available, output?
Very hard to answer. I think there's a lot of it is spent on the downtime. We also do a lot of work on some fabrication, which tends to be you're typically using a chain, a very, very complex machine equipment, and one break in the chain causes an issue.
Too much. Yeah.
Too much.
Are we going to agree on too much, or has anybody got a more statistical answer to that one? Don't feel you have to make one up. It's fine. Katrina?
It's definitely too much.
Yeah. Okay.
Taking aside the time that's required to build a beam line for spectroscopy, in particular femtosecond spectroscopy, so generation of XUV with really high state-of-the-art lasers. Besides that, the experiment is all downtown in fixing things until you get to be able to do the measurement. And actually, it's really a lot of optimization until you're able to acquire your data. And so it's few months of work, and then you may have, 1 week in which you do your experiment, you repeat it, you acquire statistics. But it's not very favorable. But this is why this is a technique which is, it needs really a lot of work before we are able to, let's say, sell it to a company.
Yes.
Which is something that it's not impossible. I mean, several of the hints also my colleagues suggested is miniaturization, integration. I mean, it can be done, but there's still a gap that needs to be filled.
Okay. And Hania, anything to add to that?
Yeah,
No.
I mean, I think just bringing the system to the status that you can do the measurement, that it's your time, right?
Yeah. Okay, there we are. So making that better for everybody seems to be a common sort of goal. Okay, I want to look ahead now at sort of trends you see shaping industry-specific spectroscopy applications. Obviously, this kind of work covers so many different fields, everything from pharma to, material science, environment, etc. Are there any big trends? If you had to pick 2 or 3 things or 1 or 2 things that you're really excited by, you think are going to be really impactful in terms of change, what would your answer to that be? Katrina, I'll go with you first, if I may.
Yeah, well, I will recycle some of my previous answer. One is indeed the development of laser technology, because we are seeing the development of new laser sources. There are new oscillator based on new material. There are all the terbium amplifier. And this is kind of it's a slow, well, not so slow, but I mean, it's a process going on. Which is changing also the price of the system that we are using for generating ultra-short pulses. And this is a trend indeed, and it's something that is going on and very positive. Maybe not to mention again the same, but machine learning, and I leave some consideration about that to my colleagues. But also, I would say that there is a trend also due to policymakers on increased sustainability. both in terms of, let's say, reducing the energy consumption of our systems, recycling materials, waste reduction, handling of chemicals. I mean, this is also a trend, which is an important one, I would say, for not only like for the lab activities for the planet and everything. And then maybe I leave some comments on some other trends. I'm always the first, so it's easy to me to.
Yeah, no, the easier ones. No. Thank
exactly.
you. Yeah, I mean, environmental, obviously, absolutely. I think we'd all concur with that. Liam, let's go to you, if I may.
This move out of the lab, we'd like to see that trend continuing. One of the issues there is in the laboratory, you've very nice analysis techniques, or there's lots of measurements that are easy in the labs. You get fantastic synchronized parts per billion, parts per trillion. As soon as you're out in the field, then you get a completely different answer. So I think we need to work. Both on developing both the analysis and the hardware that is more robust to basically the higher signal to noise that you count in the field, in order to make these or at least start approaching lab-based quality measurements in the field. It's going to take a redesign both of the electronics advances in the design of the electronics, and more redesign of the optical systems, which will by making them more robust, you probably strip out costs as well at the same time.
Okay, no, and Hania, anything? What would your take be?
Okay, so I'm excited about what we do, right? So I'm very excited about this femtosecond fieldoscopy that we started to do. And as Katerina mentioned, this is also enabled by this new advanced laser technology. So the ytterbium technology that it's now, let's say, in industrial grade, that you can put it in the lab and start to work on it. So then it opened somehow this area for us. So I'm very excited about that, because it just gives us more information that before we just could get with attosecond streaking, now you can do in ambient air. So then it brings the field result measurements to biology, let's say, and ambient air experiments. Then I'm also very excited about these new developments on chiral spectroscopy. So to detect the chiral material, I see that they have big effects in pharma industry also. And there are several groups who are pushing for higher sensitivity and selectivity. And regarding the, let's say, on-chip and integrated photonics, I think there are very nice, there has been many, let's say, new developments, but the one that I really, caught my eyes were these new developments on the lithium niobate-based, let's say, chips, that they can deliver really broadband pulses with quite good pulse energy and power. So it seems that one day we might be able to really have broadband spectroscopy, let's say, on chip, right?
Yeah. And if you were a betting woman, when would you think that could be a reality? Are we talking decades, or is it years? Or
a long way, right? But then I think long time ago, not long time, several months ago, there was this publication, I think it was in Nature Photonics or Science, I don't remember, it was on the cover also, that the scientists in Caltech, the group of Marandi, he's my collaborator also, they showed that they can build a laser on chip. Also, a group in Stanford already showed the titanium sapphire on chip. So the movement has started. It takes time, but it's good to have on chip lasers with short pulses, right?
Yes, yeah, no, absolutely. It's an interesting innovation for sure, and it'll be interesting at Photonics West whether any of this stuff gets discussed more widely next week, because I think that's always interesting as a way of kind of people showcasing something that they've managed to do in a lab, etc. In terms of implementing laser light sources, people watching this are always looking for advice. Are there any kind of succinct, I suppose sort of bits of advice or things you should or shouldn't definitely do that you would argue everybody should be thinking about before they go into a project? So what are the things people need to think about before they start implementing light sources into their work? Hania, let's go with you, if I may.
So it's really hard to give a general prescription, right? But so it depends on also, again, on the application. So if one would like to do routine measurement, then I stick with industrial, let's say, devices. But if someone likes to just, let's say, expand the horizon and so on, there are many new sources, as Katarina mentioned. Ytterbium YAG lasers are very much in place now. Chromium lasers, oscillators at 2 micron, they are doing really well. The oscillators, I mean, you can really operate them with not so much of a hassle these days. So then it depends on the type of research that you would like to do. So if the research is using the spectrometer every day, then it's better to stick with industrial grade spectrometers. But in terms of innovation, there are many new sources that open new horizons somehow.
Yeah, and I guess
in terms of brightness, repetition rate, wavelengths, right?
Yeah, and this entirely echoes what you were saying about the setup and the time spent evaluating the options before you go charging into the implementation.
Right. So, and if you want to build your spectroscopic setup, I think as all the panel members maybe did it. So as Katarina mentioned, it takes years and years, but of course then you have your unique setup, right?
Yeah.
So it very much depends on the direction of the research, and both I think are respected, right?
No, that makes sense and stuff. Liam, thoughts on that?
Yes, well, in one side's answer is difficult. In some specific areas, it's kind of maybe the equipment that supports the laser, like the temperature control, the housings, the power supplies. Very often they can be a very both significant cost, very significant draw on the power. Again, I suppose especially scientists, we sometimes focus in on the chip at the heart of the system and forget about the rest of what's on the rack above and so on. So that's very critical in some areas for sure. And the planning needs to be very careful in that sort of work.
Yep, no, fair enough. So keep an eye on your power. Katarina?
Yeah, well, I would say, as Annie said, it's difficult to give, let's say, a general advice. But what my experience is that nowadays there are a lot of, let's say, state-of-the-art techniques, spectroscopy techniques, that really requires skills. Annie mentioned before the chirality studies, and one trend in spectroscopy and in optics in general is the generation now of electric fields and light with like a specific structure, like orbital angular momentum for interacting with some sample. And this can be done with the specific optics. It can be even done in the XUV with zone plates. I mean, this requires a lot of skill. And basically, when you start like building up a project in which you would like to start a new, let's say, branch, or you want to include a different spectroscopic technique or a different source in your lab, or in your experiment, or in your company, you really need to, let's say, talk with the experts and read the literature. So there is, again, a lot that is needed in terms of, let's say, training, but this can be done with the collaboration. I mean, what we do all the time in the scientific community is to collaborate with experts. And what I see is that now I really need, like, I cannot cover the full, let's say, amount of competence that are needed with my, not either myself, but even like I have a large group with several, let's say, young PIs dealing with they cannot cover everything. So we always look for collaboration, and even for just for the spectroscopy. So new intense terahertz sources. I mean, there are several aspects, and this is, I think, it's really a value of if we share this knowledge. So establishing collaboration can be a first step to understand the capabilities of a new technique before implementing it, and if it's really suitable for your application.
Yes, yeah, no, it's interesting. I mean, obviously, electro-optics covers a range of photonic technologies, and I would say the whole sector is characterized by an ambition to collaborate, but obviously sometimes it butts up against commercial sensitivity or practical kind of considerations about kind of access or, you know, synchronizing availability, etc. So there's a question that's come in that I wanted to just pose to the team here about are there any kind of resources or information portals or things where you would direct people to go to find out what they don't know? So skill shortages, training, we know it's an issue. You've raised it this afternoon. But in terms of, is there anywhere you would recommend people go if they're looking for further insight to make this as kind of successful from the off as they can? I'm not sure if anything springs to mind. Hania, Katerina, anybody wants to answer that one for us?
Well, I think there are quite some review. I mean, based on the interest and topic, right? I mean, these days I see so many perspective review paper. Nature Method has articles on novel methodology somehow,
Yes.
so that one can find in literature, right? So I think the best is based on the question that is then one has just to go to the scientific journal. I mean, this is what I would do, right?
Yes. So do a sweep of the journal sources that you would go to and things. Katerina,
or start with ChatGPT also, right?
Yeah. So AI again. Here we go again. Absolutely. Liam, Katerina.
If I can add one point, I mean, I fully agree with Anya. I would start with a review of the literature, but nowadays, one of the positive outcome of the COVID pandemic is that there is so much material online. I mean, like there are many webinars, there are schools, there are and one can dig it. And particularly depending on the level of the information that one is looking for. But I think this is really something that in the last few years is not only the amount, also the quality. There are a lot of very good resources.
Yes. Okay. And Liam?
Maybe regarding the specific person is very often for the best results, you need to both an understanding of the spectroscopy system, whatever the laser, whatever the case may be, and of the application, the chemistry, the microbiology, atmospheric chemistry, this goes on. So it's very quickly becomes an interdisciplinary problem. So you're looking to try and, I think the academia needs to produce people who can cross those disciplines, speak the languages both sides. And that's where the groups that have done it successfully are the ones who've had the greatest success, greatest output, and are able to address real industrial needs and so on.
Yeah. Okay. No, that's good advice from the three of you. Thank you. I mean, as ever, the universal truths are there, right? Do your research before you get started. Look widely and spend some time on the setup, to try and get this right. I think that's been really useful. Thank you. We're nearly out of our sort of time at the moment. I just wanted to say a few things just to sort of conclude our session today. First of all, the obvious one is a huge thank you to our three panelists today. I think there's been some really useful, insightful advice there. So thank you for your time today. Follow their work. It's really interesting. We keep an eye on what they're up to all the time. So again, thank you very much for your participation this afternoon. Obviously, we're going to write this webcast up as a feature, so keep an eye out on electrooptics.com and in the next issue of the magazine to see a summary of what we've talked about today. If you found it useful, please share this with your colleagues. It stays online on electrooptics.com for up to a year. And thank you again to our kind of sponsor, Hubner Photonics, who has made this possible today. Final thing for me, a quick plug. Obviously, this is part of a series. We're talking to a lot of the Photonics 100 this year and getting people to work with them. We have another one. We are talking about PICs, Photonic Integrated Circuits, on February the 26th. So please sign up for that. That's going to be an interesting one about separating the reality of what they do and how they work from the potential. So where are we on that journey? And thank you again for everybody that's watching, either live or on demand. Thank you for the questions. Been a really interesting session, so thank you to everybody who's taken part. Thanks very much. Take care. Enjoy the rest of the day. Goodbye.
Bye bye.
Bye.
Bye bye.